Hello, Achha. Good morning. How are you? Welcome to Sciacademy YouTube channel. Today in this video lecture, we will be going to solve the numerical problems given in the NCERT textbook for class 11th, term 2. So, let's start the video lecture. So, as per the example 9.1, question tells that a structural steel rod has a radius of 10 millimeter and a length of 1 meter. A 100 kilonewton force stretches it along its length. Calculate first stress, then elongation, and C part strain on the rod. Young's modulus of structural steel is given 2.0 into 10 to the power 11 Newton per meter square. So, बच्चों, before starting the solution of this numerical problem, we'll observe what is given in the question. So first thing given is the radius of the rod, that is 10 mm. So 10 mm means 10 into 10 to the power minus 3 meter. So we'll convert this into meter. Second, it is given that length of the rod, that is 1 meter, and force applied is 100 kilo Newton. So, to solve the problem, let us consider that this is a rod and its one end is clamped with the solid surface, and on the other end force is applied, and which is 100 kilonewton. Because of this force, this rod will come into the tensile force. That means it will start stressing. So let us consider that the steel rod is clamped at one end and other end 100 kilo Newton force is applied. Therefore, force is equal to this much, 100 into 10 to the power 3 Newton, and area of cross section of the rod can be calculated by A is equal to pi r square, where r is given 10 into 10 to the power minus 3 meter. So area is this much. Now we have to calculate the stress. So first part is this. Okay. So stress, as you know, that can be given by the ratio of the force divided by the area of the cross section. So after substituting the values of force and area of cross section, we get the stress is equal to 100 into 10 to the power 3 divided by 3.14 into 10 into 10 to the minus 3 whole square Newton per meter square, that is the unit of stress. So after simplification, we get this and therefore this and this. So bachcho, for your understanding, I have already solved the problems so that we can move smoothly and you can understand step by step. So therefore we get that stress is equal to this much, 3.184 into 10 to the power 8. Okay, so this is the stress. Now we will calculate the elongation in the steel rod. Since we know that Young's modulus is given as the ratio of stress to the strain, here strain is the longitudinal strain and stress is the longitudinal stress. So Young's modulus, this Newton per meter square. Okay, so delta L by L can be given as delta L is equal to by Cross multiplication, we get force per unit area into 1 by A. Therefore, L can be written as delta L is equal to F by A into L by Y. Now we get this relation. Okay. After this, we will substitute the value for F by A and length of the steel rod, and Young's modulus is already given. Here Young's modulus is given for the structural steel, that is 2 into 10 to the power 11 Newton per meter square. Therefore, we get elongation in the steel rod due to the applied force equals to F by A, that is this. We have already calculated F by A, this. We will use this value F by A, that is the stress. So this into length of the steel rod divided by what? This Young's modulus. So, therefore we get this step, and therefore we obtain the value of delta L is equal to 1.59 into 10 to the power minus 3 meter, that is equal to 1.59 millimeter. So this is the part 2, elongation in the steel rod due to the applied force. Now we will calculate the strain. So strain is given by the ratio of the extension in the rod to the initial length of the rod. Therefore, delta L already we have calculated in the part B. So we will substitute the value for delta L in meter and initial length of the steel rod, that is 1 meter. After simplification, we get 1.59 into 10 to the power minus 3. You must notice here that there is no unit for strain because meter and meter will cancel it out. Okay, so it is a pure numerical value number. So therefore we get strain is equal to 0.16 into 10 to the minus 2, and in percentage we can write there is a 0.16% elongation in the steel rod due to the applied force of this much 100 kilo Newton. Okay, therefore we solve the problem number 1. Now we'll solve the numerical problem given in example 9.2. So बच्चों, let's read the problem. A copper wire of length 2.2 meter and a steel wire of length 1.6 meter, both of diameter 3.0 millimeter, are connected end to end. When stretched by a load, the net elongation is found to be 0.70 millimeter. So obtain the load applied. So in this question, we have to find the load applied. So bachon, let's solve the numerical problem. So what is given? We are given two wires. First is copper wire and second is steel wire, right? The length of the copper wire is 2.2 meter and length of the steel wire is 1.6 meter. The good thing is that the diameter of both the wire is same, 3 mm. So I have drawn a diagram for your simplicity. So see, this is the copper wire and this is the steel wire. It is connected end to end, right? So length of the copper wire is 2.2 meter and length of the steel wire is 1.6 meter and diameter is same for both. Okay, so let's LC and LS are the length of the copper and steel wire. So LC is given this much, LS is given this much, and diameter of both the wire is same. When the copper and steel wires are connected together and external load W is applied to them. So let's consider that W load is being applied to the wire. Because of this load, there is an extension, elongation in the two wires together that is given 0.70 mm. So let us calculate from the Young's modulus. We know that Young's modulus is given as the ratio of stress to strain. Therefore, stress is load per unit area and the strain is the ratio of elongation length to the initial length. Because of so this formula gives stress is equal to Young's modulus into delta L by L. So from this relation we get equation W by A, that is stress, equals to Young's modulus into the strain. Now for the copper wire, stress W by A is equal to Young's modulus for the copper wire into delta LC by LC, and for steel stress is equal to Ys into delta Ls by Ls. Ys is the Young's modulus of the steel. So since the two wires are connected end to end and some external force is being applied, so because of this external force or load, the tension in the wire will be, a tension or stress in the wire will be same. Okay, but stress in the two wires depends on their individual characteristics like their Young's modulus and length. Okay, so now let us calculate the ratio of extension in the two wires. So because of this relation we get this. Since I told you that stress in both the wire will be equal because they are connected end to end. Therefore, equating these two equations, we get the ratio of elongation in the two wires delta LC by delta LS equals to YS by YC into LC by LS. So from here we can get this equation. So you must notice this. Now, after substituting the values for Ys and Yc, we get this into Lc by Ls. Yes, you should note that all the units should be in the same form. If Lc is in meter, Ls must be in meter, and this also. So, because of that, since this Ys and Yc have the same unit, so their unit will be cancelled. So, we get the ratio of delta LC by delta LS equals to 2.5. So let it equation number 1. Now since I have applied these values, now since the total elongation is given in the question, that is 0.70 millimeter. So total elongation means delta LC, elongation in the copper wire plus elongation in the steel wire together is 0.70. So बच्चों total elongation in the two wire is given, not the separate elongation is given. It is together total elongation is given. So from this we get the equation number 2. So now we have the two unknown and two equations. So equation 1 and 2, we have the two equations and two variables delta LC and delta LS. So we can easily solve for the delta LC and delta LS. So now substitute the values of delta LC in terms of delta LS. So from here we will calculate the delta LC in terms of delta LS. So that is delta LC is equal to 2.5 into delta LS and plus delta LS, that is equal to 0.7 into 10 to the minus 3 meter, right? So after solving this, we get delta LS equals to 0.2 into 10 to the minus 3 meter. Now, after substituting the values for delta LS in this equation, we get delta LC also, that will equal to 0.5 into 10 to the minus 3 meter. You can check that if we sum these two, delta LS plus delta LC, we get total value of elongation equals to 0.7 into 10 to the minus 3 meter. So thus we get the elongation in the two wires separately. Now we will calculate the values of W. We have already known that delta LS and delta LC. So therefore we calculate W from this equation. So therefore W is equal to area of cross section into Young's modulus of the copper into delta LC by LC. We can calculate the applied load by any of the two equations. Here any of the two equations we can get the W. Whether you can calculate W with the help of copper wire or with the help of the steel wire once we get the value of delta LC and delta LS. So already we have calculated delta LS and delta LC. So therefore we can easily calculate load W by using any of the two. I have used the relation for the copper wire. So area of cross section of the copper wire into Young's modulus of the copper wire into strain of the copper wire. Therefore, area of cross section is equal to pi r square into IC into delta LC by LC. Now substitute the values for pi 3.14 and radius. Radius is given, actually diameter is given. So diameter is given is equal to 3 mm. We will calculate in meter and therefore radius is equal to 1.5 into 10 to the power minus 3 meter. So after substituting this radius here and Young's modulus here for the copper wire and delta LC which we calculated previously and the length of the copper wire. So after substituting this we get this. Now after simplification we get these values. You can solve it easily. This is just numerical and we get the value of W, that is applied load, equals to 1.76766 into 10 to the power 2 Newton, that is equal to 1.8 into 10 to the power 2 Newton. So this is the applied load on the two wires connected end to end, right? Now let us solve the numerical problem 9.3. So this is a very interesting problem and you must focus it. Let us solve this numerical problem 9.3. So problem is, in a human pyramid in a circus, the entire weight of the balanced group is supported by the legs of a performer who is lying on his back. So you can notice in this picture human pyramid in a circus. Figure number 9.5 of your NCERT textbook for class 11 term 2. So here a human pyramid is made and one performer is in the bottom on his back and all the weight of the system, I am telling the system, is supported by this performer. So load of the system means load of the individual performer except this, and the load of the tables and plaques, etc. So combined mass of all the persons performing the act and tables, plaques, etc. involved is given, that is 280 kg. The mass of the performer lying on his back at the bottom of the pyramid 60 kg. Each thigh bone femur of this performer has a length of 50 cm and effective radius of 2.0 cm. So determine the amount by which each thigh bone gets compressed under the extra load. So in the question it is being asked that find the amount of compression by which the thigh of this performer is compressed. ठीक है? So we'll find with the help of the Young's modulus relationships. So what is given in the question? It is given in the question that total mass of the all the persons, tables, plaques, etc. is 280 kg, and mass of the performer at bottom is given 60 kg. So we can find the effective mass acting on the thighs, because it 280 kg is the total mass of all the persons. Notice it, of all the person. That means it is also including the person at the bottom. Therefore, we will subtract the mass of the bottom performer. So effective mass acting on the thighs of the this bottom performer will be equal to 280 minus 60, that is equal to 220 kg. So this much mass is acting on the thigh of the performer. So let us calculate the weight on both thighs of the performer. That will be given by weight is equal to m into g. So m is the mass applied on the thighs of the performer. This is the structure of the femur in a person, human being. So total mass acting on the two thighs is equal to 220 kg. Therefore, weight applied on this femur bone, thigh bone, can be given by m into g, that is 220 into 9.8 meter per second square, that is equal to Newton total. Total weight is equal to this. Therefore, weight on his thighs is the half of this. Okay, since total weight acting on the two thighs together, so this is the total weight, and we have to calculate the weight on each thigh. Therefore, it will be equal to half of the total weight. Therefore, we get 110 into 9.8 Newton, that is equal to 1078. That means 1078 Newton weight is applied on each thigh bone of the performer lying on the bottom of the human pyramid. Okay, so 1000 1078 Newton weight is acting on each thigh of the performer at the bottom. Now, length of the thighs of the performer is given, that is equal to 50 centimeter. So 50 centimeter each thigh, right? That is equal to 0.5 meter. So radius of the thighs of the thigh bone of the performer is also given, that is 2 centimeter. So radius is 2 centimeter. We'll calculate in meter. that is equal to 2 into 10 to the power minus 2 meter, right? So therefore area of the cross section of thigh bone, okay, that is equal to pi r square. So substituting the values for pi and radius of thigh bone and taking square of this value, we get this meter square. Now we will calculate from the Young's modulus formula, that is equal to y is equal to stress by strain. Okay, so this gives strain, that is longitudinal strain in the thigh bone, that is equal to stress into 1 by Young's modulus, and Young's modulus for bone from the table can be written as y is equal to 9.4 into 10 to the power 9 Newton per meter square. Okay, so this is the Young's modulus for the thigh bone. Y is equal to 9.4 into 10 to the power 9 Newton per meter square, right? So after substituting the values for applied weight on each thigh, that is 1078 Newton divided by area of cross section of each thigh bone into length of the thigh bone divided by Young's modulus of the bone, and after simplification we get this value, and solving this we get 4.56 into 10 to the power minus 5 meter, right? That can be written in centimeter, 4.56 into 10 to the power minus 3 centimeter. Bachcho, I have solved this for you. For simplicity of your understanding, you can solve the problem after watching this video lecture by self, and if you have any difficulties, please let me in the comment box. Also tell me how did you like this video. If you don't like, or if you have any comment, please let me know. Talk to me so that I can understand your issues, and if you understand this, I will be very happy. Now let us find the fractional compression. So already I have find the compression in the thigh bone, that is equal to delta L is equal to 4.56 into 10 to the minus 3 centimeter. Therefore, fractional compression, that is strain, can be given by delta L by L. So delta L, that is 4.56 into 10 to the minus 3 centimeter divided by 50 centimeter, that is 0.09130 into 10 to the minus 3. So this strain has no unit, so that is nothing but 0.0091%. This is a very small quantity. This compression is very small. So therefore, because of this so much small compression, thigh bone of the performer is safe. So we solved the problem. Now let us solve the next problem. That is 9.4. In this problem, a square lead slab of side 50 centimeter and thickness 10 centimeter is subject to a shearing force of 9 into 10 to the power 4 Newton. Okay, so the lower edge is riveted to the floor. How much will the upper edge can be displaced? So lower edge of this slab is fixed. Okay, and a tangential force is applied that is the shearing force. This is the another parallel and opposite force is being applied. So when we shift this edge narrow face, so force is being applied on the narrow face, this face, it is being applied. So because of this slab will be displaced a little bit, and we have to calculate this displacement. So let us solve the problem. So it is given that shearing force shearing force is always along the area of the cross section, and the tensile force is perpendicular to the area of the cross section. Here the force is along the area of the cross section, right? So shearing force is 10 to 10 to the power 4 Newton, and this shearing force is applied to narrow face. So area of this narrow face is given by, this is the 50 centimeter, because this is a square slab. So this 50 centimeter, this 50 centimeter, this 50 centimeter. All sides are equal, that is 50 centimeters. So area of the narrow face is a rectangle. So this is a rectangle. So 10 centimeter into 50 centimeter is the area of the narrow face. That is equal to 500 centimeter square. That can be written in meter square by dividing this quantity by 10 to the power 4. Right. So we get area of the narrow face is equal to 0.05 meter square. Right. So when we change 1 centimeter square into meter square, we divide this value by 10 to the power 4. That will be in meter square. So mind it, because once 1 meter is equal to 100 centimeter. By applying that relationship, we can convert it into meter square. Right. Now, shearing modulus formula, we have covered this shearing modulus in the previous video lecture, and if you have interest, you can watch those video lectures. I have completed the whole chapter of mechanical properties of solids in two videos, video 1 and video 2. So I will also provide the link of those videos. You can watch those videos by clicking the I buttons in the right corner of the screen, and also through the description box, right? So this formula shearing modulus is given as the ratio of the shearing stress to shearing strain. So as I already told you, shearing stress is the force per unit area of the cross section when force is parallel to the area of cross section, and shearing stress strain can be obtained by the ratio of the displacement to the initial length, right? So therefore shearing stress is equal to this. Firstly we'll calculate the shearing stress. So applied force is 9 to 10 to the power 4 Newton, and area of cross section we calculated is this much. Therefore shearing stress is 1.8 into 10 to the power 6 Newton per meter square. Now we'll calculate the shearing strain. So shearing strain is equal to this. This is equal to shearing stress by shearing modulus. So shearing stress we calculated this much. So we put the values of shearing stress, and G for lead is given 5.6 into 10 to the power 9 Newton per meter square. So we will put the value of shearing modulus. Therefore, we get the shearing strain, that is the ratio of displacement by the length of the lead bar, lead slab. Therefore, displacement can be written as 1.8 divided by 5.6 into 10 to the minus 3 into 0.5. So after simplification, we get delta x is equal to 0.16 millimeter. Okay, so let us remind you that this is the angle theta, right? So you know that tan theta is equal to delta x by L. So this tan theta is the shearing strain. Okay, so this shearing strain, this and this gives delta x displacement equal to 0.16 millimeter, and we have to calculate this value only. So we solve the problem. Okay, now let us solve the question number 9.5, and it is very interesting and practical problem. The average depth of Indian Ocean is about 3,000 meter. So we have the Indian Ocean in the southern hemisphere, just below the Indian subcontinent, and this Indian Ocean's average depth is 3 kilometer. Calculate the fractional compression delta V by V of water at the bottom of the ocean. What is given? Bulk modulus of water is given 2.2 into 10 to the power 9 meter, and it is given as a hint that small g, acceleration due to gravity, is 10 meter per second square. So let us solve this question. So you can see in this diagram picture that suppose this is the arrangement of the lithosphere, and this is the ocean water column in which different of aquatic animals used to live here. Now I have used this picture for your understanding that the average depth of this water column is given 3000 meter, and because of this average water column there must be some pressure beneath this column due to this water depth. So each of these aquatic animal must be feeling such type of pressure because of the water column. So let us find the fractional compression of water at the bottom of the ocean. So it is given that bulk modulus of the water is given 2.2 into 10 to the 9 Newton per meter square. Acceleration due to gravity is given. So hydraulic pressure at depth is at depth of 3 kilometer can be given as P is equal to rho gh, where rho is the density of the water, g is the acceleration due to gravity, and h is the depth of the water column. So rho is the density of the water, that is 1000 kg per meter cube, g is the 10 meter per second square, and h is the depth of the water, 3 kilometer, that is 3000 meter. So after calculation we get the pressure at the such a depth of 3 kilometer is equal to 3 into 10 to the power 7 Newton per meter square. So we can calculate the fractional compression by using the formula for bulk modulus. So we know that bulk modulus is given as the negative of the pressure, ratio of the negative of pressure to the volume strain. Here is a negative sign so that we have the final bulk modulus positive, because in the hydraulic pressure there is always a decrease in the volume, so this will be negative. So this negative and this negative will make the positive. That's why we take the negative here, right? So because of the hydraulic pressure, there is a always decrease in the volume of the object placed in the fluid, right? So this formula gives fractional compression, that is minus delta V by V equals to P by V, and we just calculated the pressure at the depth of 3000 meter. So this is equal to 3 into 10 to the power 7 Newton per meter square, and bulk modulus of water is given 2.2 into 10 to the power 9 Newton per meter square. Therefore, after simplifying, we get this, and therefore this 1.36 into 10 to the power minus 2. So this is a fractional compression. It has no unit because it is the ratio of volume to volume, change in volume to the initial volume. So strain is a unitless, dimensionless quantity. Therefore, fractional compression in percentage is 1.36%. Right? That means if there is a 3000 meter depth of water, so at the bottom, so how much compression we can calculate? That is 1.36%, right? So it was asked in the question. I hope that you understand the solution of these problems. If you like this video, please like, share and subscribe the साई अकेडमी चैनल। बच्चों आप जरूर बताएं आपको ये वीडियो कैसा लगा, और अपने दोस्तों में शेयर करें, और नोटिफिकेशन बेल को प्रेस करें, ताकि जैसे ही हम आपके लिए वीडियो अपलोड करें, आपको वीडियो का नोटिफिकेशन आपको मिल जाए, और आप वीडियो देख करके आप जो है फिजिक्स को समझ सकें, और हम आपके लिए सिंपल तरीके से कैसे न्यूमेरिकल सॉल्व करें वीडियो लाते हैं, और कंसेप्ट भी आपको अलग अलग वीडियो लेक्चर में समझाते हैं। इसलिए वीडियो लेक्चर को जरूर देखें और हमें बताएं कि आपको वीडियो कैसा लगता है। मुझे बहुत खुशी होगी आपको यदि वीडियो हेल्पफुल हुआ। सो बच्चों, प्लीज स्टे ट्यून्ड एंड वॉच द वीडियो लेक्चर ऑफ साई अकेडमी। थैंक यू। बाय बाय।